Hello everyone. In this section, we will explain how GPT-2 small work in detail. Specifically, we will cover the transformer. How does it work? Because it's a decoder only, we will only cover the right-hand side. Okay. But before we start, I do need to mention that I will not include lots of the mathematical formula and equations. Okay. For example, I won't explain the calculation for this attention calculation. What's the purpose for this uh, Q and query key value matrix, and how does this matrix manipulation work? But I will do this in a high level, okay? And how does this multi-head attention work to this concatenation? I won't cover everything, but I will try to make it at a high level. Okay, we will obviously still leveraging this source code, which lives in this model file, model.py file, and then at the same time we will also look at other tools like these visualization tools for this one and also this one. All right. Um, yeah, let's start from this visualization tool. Uh, we can see there are multiple layers, right? It all, even this one is very clear. There are multiple layers. The first step is do this positional encoding and this input embedding, and then go through multiple layers of this transformer, and then return the output. Okay, and then you can see over here in the encoding, essentially you do two things. One is this token embedding and then positional embedding. Okay, if you look at over here, they simply are adding these two together, and then form this total input. Okay, and then it will then fit into multiple layers of these transformers. In the GPT, in another GPT, it's only three layers. Transformer 0, 1, and 2, but in the GPT-2 small, it has 12 layers. Okay, but it just more layers, more parameters, but structural architecture wise, essentially the same. Okay, and then we need to break down inside the transformers and see how does multiple components are connected. To be more specifically, you will see this layer normalization appear before the major other components. You do layer normalization before you feed them into the self-attention block. You also do the layer normalization before you send them to your feed-forward network, your multi-layer perceptron. You do another layer normalization at the output. Okay, this layer normalization, generally speaking, it will help you stabilize this process. Okay, it will just make the mean value, all the values for the distribution. The mean value will be 0, and the standard deviation will be 1. Okay, so that this is a crucial part of the neural network. And then after the normalization, okay, so the input and go to this normalization. In the normalization, it will first go through this attention calculation. You will see all the calculation over here, the Q, key, V, all the weights and bias, and then matrix manipulation, and then generate the output. It pretty much do in this piece to calculate this attention, and then apply this piece of calculation to calculate the attention. Obviously, there's a stage for the multi-head attention, but it simply do a concatenation. It just add everything together and then give you the output. Okay, and then in the output, you will also do another kind of projection. Okay, it's something called this residual connection. What it does is simply adding two blocks, the attention block and also the original input block, layer by layer. This residual connection, it just add two of them together. Okay, and then like we mentioned before, another layer normalization, and then go through this multi-layer perceptron or feed-forward network. Okay, so what it does, it will just do one thing, is to expand from this existing dimension to a higher dimension, and then apply this activation this activation is a non-linear function. It's a glue activation, and then it will project it back to compress it back to the original dimension. Okay, and then you have your output, and then you do another residual connection. Okay, and then you then go to the next layer of your transformer block. That's pretty much the end-to-end process. Okay, just to reiterate, you have your input, you go to layer normalization. Oh, it's actually over here. Layer normalization, multi-head self-attention, and then you residual connection. Do another layer normalization, and then multi-layer perception, and then do another residual connection, and then go to the next layer of your transformers. Okay, we can also see over here. Okay, in the transformer explainer website, in the beginning we have your input. Okay, you can have you're adding your token embedding and positional encoding, and then you can look in details how does these uh, weights and bias and doing it all together and do this calculation and give you this tension value, which is very cool. You can visualize in this way. After this calculation, you get all your attentions. Okay, you see the dot product and scaling and mask, softmax, which is just this equation. Okay, and then afterwards, it will fit into this multi-layer perceptron. It will do the activation function, which is a glue, and afterwards, it will do another. It will give you the output basically, but the output is logits, right? Output is logits. It's not the probability yet. It will go through this sampling process and then give you the final output. Okay. Let's quickly look at this piece of code, which will again pretty much do the same thing. Okay. This is an entry point, the model file. You can see this big piece. One is to this token embedding. The other is to a positional encoding or embedding. You simply add them together. You get the input, and then you go to the transformers. In the transformers, you have this for loop, right? There are 12 layers. If we look at the hyperparameters, there are 12 layers. So it will do this multiple times, right? It will go through this block multiple times. Okay, and then finally do another normalization, and then do a final output. You get the logits. Okay, let's go deep into this individual block. Okay, so in this block, you can quickly see it has a couple of things. One is this attention, another is multi-layer perceptron, right? But before the data or the input is fit into individual components, you do this normalization, right? This is your normalization function, and then you do your attention calculation. Right? Let's look at this attention calculation. It has mask your attention weights, so the input will no longer see the future tokens, which is helpful during training, but it won't do much in the inference stage because you actually don't know the future tokens. It will do this autoregressive predict the next token. Okay, and this is basically the main piece. This method will just implement this equation over here. Okay, this multi-head attention, and then which include the softmax and then matrix manipulation. All right, and this is the main one to grab everything, to combine everything together, including to distribute your parameters, Q, K, V, distribute them into multiple heads, and then do your calculation. Okay, and then you have your calculate the attention, multi-head attention. You need to merge them. You do another projection and then return. Okay, that's individual attention layer. Okay, and then you see this one, x plus a. This is pretty much the residual connection. Okay, residual connection at here. Before you go to the next, see this one, from the self attention to multi-layer perception, you will go through this residual connection, which is basically adding them back. Okay, and then feed them into another normalization multi-layer perceptron. If we look at the multi-layer perceptron, you will see it will do a two kind of linear projection. One is to expand or scale out to a higher dimension, and then go through this activation function, which is a nonlinear one. Yeah, a nonlinear one. And then let's quickly go back. Okay, go back, and then it will project it back. Okay, look at this one. This one is basically multiplied by 4 because this state is this end state is 4. Now let's find it. This one. Okay, you kind of multiply it by 4, so it will expand from the existing dimension to a higher dimension, multiply by 4, and then project it back. Okay, that's a whole block. You do another residual connection and then return the output. Okay, and that's the individual block. After you do this, you do another normalization, you get the output. Okay, this is pretty much the this high level walkthrough for the code level. It's just amazing. Just around 200 lines of code. It just implement everything end to end. And very elegantly. Some of the strategy they have used, including some of the caching. So I think this one, they save the past states, right? So they won't redo the calculation. And obviously in this code, you see lots of shape have been changed. That's all because it's like a multi-dimensional vector or multi-dimensional matrix calculation and manipulation. Okay, if you do want to go very, very deep, a couple of things you can do. You can even look at the original paper. There is this attention visualization to explain how does individual token attend to all other tokens. Okay, there's another one over here. There's another one over here. I also recommend you to go through this again because it does a very good representation for the visualization process, how our individual pieces are connected to each other. Obviously, this one highly recommended. Look at the beautiful animation, do the calculation, and give you the final output. Okay, all the attention value, all the attention scores, and so on and so forth. All right. I will probably stop it over here. And thanks for watching. Bye bye.